I got 2 minutes. So make sure you do your seating chart and make sure you're ready for an eye clicker. Make sure you have your eye clicker ready to go. All right, so time to start. A really terrible, this is a real 4th grade level joke. What did one toilet say to the other toilet? You're looking flushed. That is like classic 4th grade, right? Terrible. Okay, so get your eye clickers out. On that note, get your eye clickers out. We have a few more. Let's see, we're gonna start on, yep, that one. Okay, here we go. So I am giving you a picture of lactose. Tell me, what is the glycosidic linkage? Make it a little bigger for y'all. Oh, I have to start. Okay. Remember, 1 minute. Okay, so we got 45 today. All right, so turn and talk to your neighbors. $30 seconds. Well, no, we said 45 seconds. We're changing it, right? 45 seconds to chit chat. Okay, 45 seconds. All right, so what did we say? All right. Okay, so we have a beta 1,4. So it looks like we definitely went up. So let's talk about why that is a beta 1,4, right? So what was the first thing you did? You look for the anomeric carbon. How do you find the anomeric carbon? It's the carbon that's bonded to 2 oxygens. So right here is my anomeric carbon, because here's oxygen 1, here's oxygen 2, right? So if I have another carbon bound, then that other carbon gets number 1. But is there a carbon bound to this anomeric carbon that's outside of the ring? No. So this one gets number 1, and it's participating in the glycosidic bond, so I don't need to go through and number everything else. Okay, find my other anomeric carbon, also bound to 1, 2 oxygens, but what do you notice? Is this anomeric carbon participating in a glycosidic bond? Nope. So we're only going to have 1 alpha or beta, right? So there's no other carbon bound to this anomeric carbon outside of the ring. So we give it 1, 2, 3, 4. So that's a 1, 4. So we know that part. Now, where does the alpha or beta come from? You look at the anomeric carbon that's participating in the glycosidic bond, whether it's 1 or 2. You look at the carbon that is outside the ring, the highest number carbon that's outside the ring, and you compare it to the orientation of the glycosidic bond. So CH2OH is up, glycosidic bond is up and up is beta or cis, right? But we don't say cis in sugars, we say beta. Okay. All right, let's try another one. What is sucrose? What is sucrose? Yeah, you have your notes. Right? Remember, sucrose is that table sugar. Please make sure your masks are on. Okay, got about 5 seconds left. Okay. Turn, talk to your friends. Give yourself 45 seconds, so keep discussing. Okay, 10 seconds. Make sure you ring in again. Okay, so what did we say? It should have been B. That's right, it should have been B. Oh, it's much better when y'all talk to each other, right? So sucrose is a disaccharide, right? So you could automatically eliminate D and E. And then this is one of those things, you know, I told y'all there are some of those sugars that you have to go in and learn, right? This is one of them. Go and learn your disaccharides and your polysaccharides. Go learn them, okay? Every now and then there are some things that I tell you, you just got to learn, like functional groups. You just got to learn them, okay? All right. We got 2. I actually have 2 more. So this one and 1 more. Okay. Why are oligosaccharides important? 10 seconds. Okay. Turn and talk. Come up with another answer. Keep those masks up while you talk. The whole point of the mask. Okay. Don't forget to ring in again. Ring in again. That's 45 seconds. Make sure you rung in again. Okay, so let's go through each statement before I reveal the answer. Oligosaccharides are the main structural materials in plants. True or false? False. How could I make this statement true? Not oligo, but poly. Polysaccharides are the main structural materials in plants, right? Which polysaccharide? Y'all not studying your polysaccharides. Which one? Cellulose, right? Cellulose is structural, yes. Okay, oligosaccharides are the major energy source for plants and animals. True or false? False. How could I make it true? Polysaccharides are the major energy source for plants. That's really starch. And what is starch? Amylose and amylopectin. And animals, it is glycogen. Oligosaccharides are a form of energy storage for animals. It's the same thing, right? Poly, glycogen. Okay, D, oligosaccharides on cell surfaces allow immune cells to distinguish a person's cells from the cells of another organism. True or false? This one's true, right? What's an oligo? What does oligo mean? 3 to 9 monomers of sugar. How many are on the surface for type O? 3. How many for type A? How many for type B? 4. Okay. You'll have to go learn those. All right. So question 5, it should have been D. It should have been D. So at least we went up. Okay. No, that is no, I got one more. All right. Last one. Select the false statement. Okay, about 10 seconds left. Okay, turn, talk to the people around you. Looks like we got this one. Lots of people ringing in quick on this one. 45 seconds. Make sure you click in again. Don't forget. Okay. So what did we say? So it is B. It is B. So if we look, individuals with type O can donate blood to anybody because type O is called what? Universal donor. So A and B can't be correct if you have two different blood types, right? So to make statement B correct, it would have to say people with type O blood can donate to anyone, right? Or what else? How else could you do that? If you left it A, type A blood can donate to who? They can donate to A. They can donate to AB. Okay, you have to be able to do that too. So AB can accept blood from anybody. AB is called the universal recipient. UNIV. Universal recipient. Okay. Individuals with type A have type A markers. Yeah. Individuals with type AB blood have both A and B markers. Yeah. Okay. Questions? Good. All right. So let's start chapter 7. Woohoo! So today is Thursday. What's happening next Thursday? Exam day. It's another exam day. Are you ready? You got a week to get ready. So make sure you are ready for next Thursday. Okay. All right, so we are starting chapter 7. Chapter 7 is all about gas laws, solubility, and how that applies basically to cells and cell membranes. So if you look on your best friend, pull up your best friend. There's some things that you're going to need on your best friend. So do you see at the very top of the screen there? I have some equivalencies listed. 1 ATM is equal to 14.7 PSI is equal to 760, 8 millimeters Hg is equal to 101,325 pascals, right? So these are all given to you. They are on your equation sheet. Can you find them? So it's on this sheet, it's on this page, kind of in the middle, it says pressure. Yeah. Okay, that's what you're going to need. So I listed it up here because we're going to convert. We're going to do lots of conversions. So you have to get really comfortable with those. I want to make sure you can find them on your equation sheet. Now, before we do some example problems, I guess we could do these first because these are just conversions. So there are many different pressure units. Right? Everybody's got their own pascals, millimeters mercury, PSI, everybody's got their own. So you have to be able to convert between all the different ones. So all you have to do is write what you start with. So in this case, we're starting with 1,131 pascals. And what do we want to get to? We want to convert the pressure readings to ATM. What does ATM stand for? Atmospheres of pressure. So if you're at 1 atmosphere, you're at sea level, right? So basically all of Louisiana, especially down here, is at 1 ATM because we are at basically sea level. We're below sea level in some places, right? Okay, so how do we do this? This is just a simple conversion. Whatever's on top that you want to get rid of, what do? Put it on the bottom. And what do we want to get to? We want to get to ATM. So do we have a conversion that will link ATM and pascals? Yes, we do. What is it? 1 ATM is equal to 101,325 pascals. What do we get? How many sig figs? So you're given 6 significant figures technically. So technically, you do not count significant figures in conversion factors. You only count significant figures in values, initial values that you are given, values in the problem, but you do not count significant figures in conversions. So really our answer should go, how many significant figures? How many are here? 6. So what's my answer to 6 significant figures? 1.00. It's not a perfect 0006. Okay. What's my unit? ATM. Okay. All right. B. 762 millimeters of mercury. So why do we do this? What does millimeters of mercury have to do with pressure? You can create this device to measure pressure. You put mercury inside of a dish, and then you basically put a test tube upside down on top of that mercury. And the force from the air pressure is going to push up the mercury into the tube. And so we measure the height that the mercury will go up the tube. And if you're at 1 ATM, it goes up 762 millimeters, right? So it's an old-timey way to do it, but it works. All right, so we want to get rid of millimeters mercury. Do we have a conversion factor between millimeters mercury and ATM? Yes, we do. What is it? In 1 ATM, we have 760 millimeters mercury. So what do we get? 3 sig figs, 1.00 ATM. Okay, how about C? 14.6 PSI. PSI is pounds per square inch. Do we have a conversion factor that will convert PSI to ATM? Yep. 1 ATM is how many PSI? 14.7. And what do we get? 0.993 ATM. Ooh, I missed my ATM. So all of these are about 1 ATM, right? Okay. So before we go on to the next page, I want to talk about a few things real quick that are going to get you through this chapter. What's going to get you through this chapter? You need to know 2 main things to get you through this chapter. Number 1 is the ideal gas law. What's the ideal gas law? I call it PIV-NERT. PV is equal to nRT. So using this equation, you know that in order for this equation to work, the left side of the equation must equal to the right side of the equation, right? Think about algebra. What does P stand for? Pressure. What is V? Volume. What is N? Number of moles. Okay, what is R? It's a constant. That constant is on your, it's on your equation sheet, I do believe. Where did they put that one? Did they not give you that? I'll always give it to you. I'll have to go in and build it in because I don't see it. I will go in and I will put it in. Okay, what's T? Temperature. Okay, so this is just algebra. If I have a container and it is filled with a gas, okay, if I change the volume of that container, if I make the volume go down, in order to make this equation work, what would have to happen if I told you you cannot change temperature, you cannot change number of moles? I'm telling you, you can't mess with this side of the equation, that we're going to hold all this stuff constant. If volume goes down, what would have to happen to allow this equation to still work? Pressure would have to go up. That's exactly right. Because the left side has to equal to the right side. So if there are only two things of value on the left side, if one goes up, the other must go down so that they equal out, right? Okay, so the same thing is true if we look at things on opposite sides of the equation, right? You'll have a different relationship, but it still works. So what if I increase volume, but I tell you to hold pressure constant? So number of moles or temperature could do what? Go up, right? So let's say we're going to hold moles and R constant. So what would have to go up? Temperature. Because if the left side gets bigger, the right side has to get bigger in some way, shape, or form. So if you think about this in pure algebra, you are going to be able to predict all of your answers. It's really awesome. This one equation, PivNert. No PivNert, okay? No PivNert. So that's one thing. The other thing is, if you watch the videos, right? There are all these gas laws named after all these scientists who found them, right? I'm going to combine all of these gas laws into one equation. That equation is PV over T is equal to PV over T. The first one is your initial, so we put a little I, and the last one is final. So basically what this says is, if you start out with these three initial conditions and you change one of the conditions, what's going to happen at the end? What's going to happen to the final stuff, right? So the way that I remember this one is always, 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 always put your peas and vegetables on the table, right? Put your peas and vegetables on the table. So how does this work? How can we use this? Well, I can look and I can say how these things are related to one another, right? There are lots of different gas laws. There's Boyle's. Do you have to know the name of the different laws? Yes, you do, but I'm going to teach you how to remember this. Did I tell you the tricks in the video? I think I did, didn't I? Okay, so Boyle's law tells me that pressure is inversely proportional to volume. Well, can I use this equation to understand that relationship? Well, sure, because if all I'm worried about is P and V, I can do PV over T, right, is equal to PV over T. But we don't have to worry about T. It's all my peas and vegetables on the table, right? So if pressure goes up, what's volume going to do? Volume's going to go down, right? It's just algebra. It's just algebra. But if you remember peas and vegetables on the table, and then go and learn your different ones. So I told you the little mnemonic to remember Boyle's law, right? There's the kid who wanted to go to the high school prom, and he looked in the mirror and he saw this great big boil on his face, and he was really peeved. Peeved, right? Boil and PV. Those are, you just have to remember it's inversely proportional. But if you remember the peas and vegetables on the table and PivNert, you're going to be good. Okay, Charles's law. What's Charles's law? And this is not who my Charles was named after. Charles's law relates what two properties? What is it? Volume and temperature. And I know it shows volume and temperature, but I remember it as TV because I remember TV shows with Charles, like Charles in Charge, like Charlie's Angels, right? That's how I remember it's TV. But if you remember peas and vegetables on the table, you can remember the V goes on top of the T, right? Okay, what's the last one? Gay-Lussac's. Gay-Lussac's, and Gay-Lussac's is the last two, which is pressure and temperature, right? Pressure and temperature. And that one you just kind of have to remember. Sorry, I don't have a fun one. Okay, so if you remember that, we're gonna be able to solve every single problem super easy. All right, so suppose you have the same amount of gas in two containers, C and D. Both containers are at the same temperature. Container C is half the size of container D. Which gas is at higher pressure? We're going to solve this a couple of different ways. I want to do the math way that I just showed you. So what am I going to use here? I'm going to use Pivnert. Okay, this is telling me, suppose you had the same amount of gas in two containers. If it's the same amount of gas, what's constant? Moles. So N is constant. Both containers are at the same temperature. What else is constant? Temperature and N is constant. So in this equation, this whole side of the reaction, the equation is constant. So if container C is half the size of container D, what happened to volume? Volume goes down. So if volume goes down, pressure goes up. So if container C is half the size, which gas is at a higher pressure? Container C. Right, and container C, right? Because number of moles and temperature are constant while volume decreases. Therefore, pressure must increase. So we did that the mathematical way, right? So let's talk about this just logically without numbers and all that, right? If I have the same amount of gas in two containers and I take one of those containers and I shrink it to half the original size, you have the same number of gas molecules. So remember cars on the street? Remember we talked about that with reactions? So basically what you're doing is you're putting the same number of cars on a smaller grid to drive in. So what are they going to have more of? What happens when you get more cars on the street? More collisions. Do you know what pressure is? Pressure is defined as collisions against the side of a container. So just like you're going to end up hitting other molecules, you're also going to end up hitting the sides of the container. And that's the definition of pressure. So because you shrink the size of the container while keeping the number of moles constant, you're now increasing numbers of collisions with the size of the container. So you could also say container C because you are increasing the number of collisions with sides of the container. NER, which is equal to pressure. So you could have answered that even other ways, or even other ways to answer that, but it gives you an idea. Okay. All right. So the next one, when you swim underwater, the pressure of water pushes against your chest cavity and subsequently reduces the size of your lungs. For every 10 meters below the water's surface, the pressure exerted by the water adds 14.7 psi to atmospheric pressure. So if you're underwater, you have atmospheric pressure plus the pressure at whatever depth you are. So you have to take into account both. So the total pressure 10 meters below the surface would be 29.4 psi. Now, you have a lung volume at 6 liters. You're at sea level right now. So basically everybody here has about 6 liters of volume inside of your lungs. What would the volume be of your lungs when you are at the bottom of a pool that is 5 meters deep? Okay, what we're given in the problem is 10 meters. So anytime you see a condition, you see a problem where they say initially, this is what it was, and now finally, this is what it is. Initial, final, this is peas and vegetables on the table. Okay, that's when you use peas and vegetables. So let's do that. If we're going to do peas and vegetables, what I like to do is I like to take a second and pull all the information that I can out of the problem and then try to go complete the problem. Otherwise, I feel like it's too much, right? So we know we're going to have initial conditions and final conditions. So let's go pick out our initial conditions. Our initial conditions were at sea level. Sea level. So what initial conditions are we given in this problem? Six liters of what? What parameter is that? Volume. So I say VI, so I keep track of things, is equal to 6 liters. Do we have another initial condition? You're at sea level. What's something we just talked about just a minute ago about sea level? Sea level is equal to 1 ATM. So my PI is equal to 1 ATM, but was I given anything in ATM in the problem? No, what's the pressure unit I was given in the problem? PSI. So can we go ahead and convert that real quick to PSI? What's 1 ATM equal to? 14.7 PSI. Okay, now I want to talk about my final conditions. What are my final conditions? Like what's the difference between initial and final? Initial is at sea level, final is at is at 5 meters. 5 meters in the water. Right, 5 meters deep. Whoa. On my paper. Okay, so if we're at 5 meters deep, what do we know? That it's what? Okay, so we know at 10 meters, we know the pressure at 10 meters. So eventually we're going to know the pressure final at 5 meters, but we don't know it yet. So let's go solve that. How do we get pressure final? Let's go solve that. We know at 10 meters, it's what? It's what? At 10 meters. Okay, so you can do it that way, but I want to figure out how we got there. So what's the pressure from water at 10 meters? Water at 10 meters. You add how much? It adds 14.7 psi to atmospheric pressure, right? So you got 14.7 psi per 10 meters, right? But am I at 10 meters? No, I'm at 5 meters. So what I can do is I can just multiply by 5 meters, right? So this is my water at 10 meters. So this gives me what? Put in your calculator. .34 psi. Is that what y'all got? Okay, so this is water at 5 meters. But you have to add that to what? To sea level pressure, right? Sea level. So sea level pressure, we said, was 14.7 psi. Yes, ma'am. 7.35. Thank you. So what do you get? 22.005. Okay, and that unit is PSI. So we actually had to do a little bit of math in order to figure that out. So this is our really pressure final. Our pressure final is a combination of both water and air pressure. Okay, so we can put that over here at 22.05 PSI. Now, what else do we know or are trying to find out? Do you see in the question, what would the volume be of your lungs, right? So our volume final is our unknown. Once you get close to the bottom of this, it gets crazy drawing. So our volume final is what we're trying to solve for. So what am I going to do for my actual work for the problem? Gosh, we've done all that. We haven't even done the problem yet. What do I do? Plug it into what? Which formula? Peas and vegetables on the table or Pivner? Peas and vegetables on the table, because that's all of my initial final. So I got peas and vegetables on the table, peas and vegetables on the table. Do I need to worry about temperature? No, so you can actually just get rid of that because temperature is constant. It won't always be, but for this problem it is. So now plug in your values, P, so this is PI, this is PF, VF. Okay, so my initial volume is 6 liters. My initial pressure is 14.7 PSI. My pressure final is 22.05 PSI. And my volume final is my unknown, so I'll call that X. Or you could call it VF. We'll do that. We'll call it VF. So this is really important. You need to make sure that your units are the same. So PSI will cancel, right? Because all you're going to do is divide both sides by 20.05 PSI divided by 20.05 PSI. So your PSIs cancel. What unit are you left with? Liters. So all of this cancels. So what do we get for liters for volume final? 4. So we went from 6 liters to 4 liters, just going 5 meters into the water. It's kind of crazy, right? Yeah. Questions? Good? Okay. All right. If I can scroll up, come on. Oh, there's the top. Okay. All right, so we have another one. A gas has a volume of 10 liters at 0 degrees Celsius. What is the final temperature of the gas in degrees Celsius if its volume increases to 25 liters? Pivner or peas and vegetables on the table? Peas and vegetables on the table. So I know that I'm going to have initial and final conditions. So tell me about initial. I know volume, right? What's my volume initial? 10 liters. So we did that. How about this? T initial, which is 0 degrees Celsius. Now, be super insanely careful here. Sometimes I will ask for it. I will give you values in Celsius and then ask you for an answer in Kelvin. So you have to make sure that what you're given and what your answer is in is the correct units for temperature. In this case, I'm asked, what is the final temperature of the gas in degrees Celsius? So I can keep in Celsius, okay? All right, so tell me about final. Do I know my volume? Yes, volume final is 25 liters. Do I know my temperature final? No, that's my unknown. That's what I'm going to solve for. So y'all told me put my peas and vegetables on the table, right? PV equals to PV over T equals to PV over T. Do I need all of the parts of that formula? No, isn't this so nice? You don't have to know which law to use to do the math, right? All you do is put your peas and vegetables on the table and then eliminate things that you don't need. So what do I not need? What can I erase? Pressure, because it's held constant. Okay, all right, so now I go in and put my I's and F's, right? I's and F's. So volume initial was 10 liters. Temperature initial was 0 degrees Celsius. Volume final, we said 25 liters. Temperature final is our unknown. What do you do to solve for your unknown? Isolate it by itself. So what could you do? Cross multiply. Most people will say cross multiply, right? So then you get, we'll do both ways, right? So then you're going to get TF times 10 liters is equal to 25 liters times 0 degrees Celsius. So what do you get? What's the problem? What happens when you multiply by 0? You're gonna get 0. Does that make sense? It doesn't make sense. This is why you can't always use Celsius, right? Because in these equations, if you have a temperature of 0, you can't do the math. So what do we have to do here? Convert it to Kelvin, but then before you give your final answer, do what? Convert it back. So how do we convert degrees Celsius to Kelvin? So we add, so we take our degrees Celsius, we add 270, what? 273, and we get our temperature in Kelvin. So this is no longer going to be 0 degrees Celsius. It's going to be what? 273 Kelvin. Now I'm going to divide by 10 liters. What do you get for a temperature final? It's going to be a big number. 683. Is that what y'all got? 82, 83. Does it round? 82.5 rounds up to 83. So 683 Kelvin. But can you leave it in Kelvin? No, what do you have to do? Subtract 273. What do you get? 410 degrees Celsius. So to double your volume, you have to get pretty gosh darn hot. What's boiling in Celsius? Celsius is cool because 100 degrees is boiling and 0 degrees is freezing. So if you start out initially at 0 degrees Celsius, you're at freezing point of water, right? Your temperature final to go from 10 liters to 25 liters, you had to go to 410 degrees. That's really hot. It's really hot. Okay. All right. Assuming no air can move in or out, what happens to the volume of a hot air balloon as the air is heated? I want you to use what equation? Peas and vegetables on the table or Piv nerd? Piv nerd. Okay, so assuming no air can move in or out, what does that tell me? Something's constant. What's constant? Not volume, because this is asking what happens to the volume. Amount of something is number of moles. So you hold in constant. So constant number of moles. What happens to the volume of a hot air balloon as the air is heated? So don't worry about N. R is a constant, so we're not going to worry about that. So what happens to the volume if a hot air balloon is heated? So what does that do to temperature? We're going to increase temperature. So what do we have to do on the other side? Increase. Have you ever seen a hot air balloon being inflated? Like, you know, those big, the big ones that they go on, you know, big events, and it's really cool. They feel the sky, right? When they have that little fire underneath the big old balloon's deflated, right? But then they put the fire underneath and all that hot air goes into the balloon. That's why they call it a hot air balloon, right? And what happens to the balloon? It inflates. So what happens to the volume of the balloon when it was cold? Deflates, right? You heat it, it inflates. The volume gets bigger, right? Okay. All right. Let's see. Oh, this is really cool. Okay. An Ambu bag. This is used in emergency resuscitation. So this is a good practical application of all these gas laws, right? So if you squeeze this bag, what you are in effect doing is that you are decreasing the volume, right? So if I decrease the volume, Piv nerd or peas and vegetables on the table? Piv nerd. Okay, so if we decrease the volume, what happens to the pressure on the inside of the bag? Increases the pressure. So what happens to the inside? Pressure increases. How does this help a patient who's not breathing on their own? It pushes the air into the patient's lungs and inflates the patient's lungs. It's exactly right. So there are lots of applications of gas laws in the medical field. This is only one of them. So how does this help, right? So the air is forced under high pressure into patient's lungs. Patient lungs, inflating them, inflating the lungs. Right? What happens when you let go? You release the pressure. What happens? The bag's going to reinflate, right? And then you just keep doing it. There's a really cool video on how the valves and everything work in the Ambu bag. I think I posted it. So if you look at the chapter 7 material, I'm pretty sure I posted it. At least I wanted to. I'll check when I get back to my office to make sure I did. But there's a really cool video on it. It's really interesting. Okay. Here's one, not so medical, but it's a good example of gas laws. So we have 100 milliliter bubble of hot gas at 225 degrees Celsius and at 1.80 ATM. It escapes from an active volcano. What is the new volume of the bubble outside of the volcano where the temperature is minus 25, so this is below freezing, and the pressure is 0.8 ATM? What are we using? Peas and vegetables on the table or Pivnert? Peas and vegetables on the table. So I need to go find my initial and my final conditions. So what do I know? Initially, what do I know? I know my volume initial, which is 100 milliliters. What else do I know? What? So we did this one. What is this? Yeah, what is degrees Celsius? Temperature. 225 degrees Celsius. How about this one? Pressure initial, 1.80 ATM. Okay, what do I know about my final conditions? Do I know my volume final? Oh, no, we don't. Okay, do I know my temperature final? Yes, right here, minus 25 degrees Celsius. But what do we know about Celsius? Can we use Celsius to do the math? No, let's convert it. So let's convert both of these. 273, what do we get? Should be 498, is that right? Plus 273 and 248. Okay, so we did that, and now we need this very last one. What is that? Pressure final. And both of the pressure values are given in the same unit, so we're okay. So peas and vegetables on the table, right? Do we get rid of anything? No, we don't. We have to use it all, and that's cool. Okay, so let's do the initial first. My pressure is 1.8 ATM. My volume is 100 milliliters, and it's actually 3 sig figs on the 100 milliliters. Over my temperature initial, which is 498 Kelvin. Pressure final is 1.8 ATM. Okay, my volume final is my unknown. And my temperature final is 248 Kelvin. So what I like to do is just flip this. So I'm going to put 248 Kelvin on top, 1.80 ATM on bottom, and they cancel out here, which you do to one side, you do to the other side. So this is 248, okay, over 1.80 ATM. My Kelvins cancel, my ATMs cancel, I'm left in milliliters. What do you get for math? What do you get? Anybody? Got it? Go for it. 108.4. Anybody else get that one? I got 112. 112. Okay, so I got 112. What are my units? I'm left in milliliters. I don't know where that came from. It's equal to VF. Okay, good. Okay. All right, here's another one of those explain ones. A cylinder of compressed gas empties. The pressure inside the cylinder decreases. Now think about a cylinder. Is a cylinder the same thing as a balloon? No, like if you have a business that does helium balloons, right? Your cylinder that contains the helium, is it ever going to change volume? No, it's a fixed volume container. That's what a cylinder is. So if you see that, you know a cylinder is a fixed volume. A balloon is a adjustable volume. So if it's a cylinder, you're going to have a constant, right? Volume is constant. If you have a balloon, the balloon can change. Okay, so you have this cylinder of compressed gas. As it empties, the pressure inside the cylinder decreases. Explain why this happens using the ideal gas law. So this one, I actually told you, are you going to put peas and vegetables on the table or are you using Pivnert? Pivnert is the ideal gas law. Okay, so what are we going to hold constant? We're going to hold volume constant. What else are we going to hold constant? Can we hold in constant? As a cylinder of compressed gas empties, that means like, okay, if it's a helium balloon tank, I'm starting with a full tank and I filled 50 balloons. Do I still have the same number of moles in the tank as I did initially? If I've already filled 50 balloons? No, I've emptied some of the gas particles out. So my number of molecules is going up or down? Going down, right? I'm losing gas particles. I'm emptying the cylinder. Okay, R is a constant, so we don't have to worry about that. Did we talk about temperature at all? No, we didn't talk about temperature. So we're going to hold all that constant. Tell me about the pressure inside the cylinder. What is pressure going to do? Pressure is going to go. Pressure is going to go down. Y'all are right. Pressure is going to go down, right? Because you have to have both sides of this equation equal. So if one side of the equation goes down, the other side of the equation must go down. If the things are on the same side of the equation, they're inversely proportional. If there are two things on opposite sides of the equal sign, they are proportional. So write that down. That's probably a good thing to write down. So if you have two variables on the same side of the equation, they are, same side is inversely proportional. Proportional, right? And then the opposite is if the two variables are on opposite sides of the equation, they are proportional. That make sense? And I want you to also think about it in terms of cars on the road. What did we do in essence? We didn't change the size of the city, right? What did we do to the cars? We decreased the number of cars on the road. If you have fewer cars on the road, are they going to have the same number of collisions? No. So pressure is going to decrease because pressure is collisions. Okay. All right, y'all got that? Okay. Not too bad, right? This is not too bad. Remember your peas and vegetables on the table, and remember Pigner, and you're going to be okay. But do learn the people. Don't forget about that. Okay, so now we're going to talk about liquids and solids. What have we talked about so far today? Gases, right? So now we're going to talk about how liquids and solids interact with one another based on their chemical properties, right? Do you remember how we talked about water? And tell me about water. Why does water have its particular unique properties? Tell me about water. How many times are we going to draw water in this class? Everybody loves to draw water, right? So you have an oxygen molecule and atom, and the oxygen atom is hooked to two hydrogens, right? If I draw water, is that a good enough representation of water? I know it's bent like that because it's got lone pairs, right? What else do I know about water? Oxygen is very what? Electronegative. It's like next door neighbors to fluorine the floozy, right? So what is it like to do with its electrons? It hogs them. It even hogs hydrogen's electrons. So then what happens to the water molecule? It becomes what? What does this mean? It becomes polar. So we have a portion of the molecule, the hydrogen, that is partially positive. These are partially positive, and what's water? Partially negative. That's what that delta sign tells you. It's partial. It's not a whole -1. It's not a whole +1. It's partial. So now what do we say water is? Water is polar. Therefore, water is attracted to water, right? You have the hydrogens from one water molecule attracted to the oxygens from another water molecule. That's what gives water its unique and amazing properties. So this is an example of an attractive force between molecules, right? And so this is an example of the things that we are going to talk about today. So what types of attractive forces exist between all molecules? Every single molecule on the planet is going to be attracted to other molecules. There is attraction between all molecules, whether they are polar or not, but it's very, very weak. If you watch the video, what attractive force is it? How many people watch the video? You know if I want to know the answer to that. London dispersion forces. So London dispersion forces are called temporary dipoles. Water has a permanent, that's not how to spell permanent, dipole, right? Water has a permanent dipole. Water is always going to have a partially positive section and a partially negative section. But not every molecule is polar, but every molecule has London dispersion forces. And the reason that every molecule has London dispersion forces is because everything has electrons, right? Now, electrons, you know, when you look at an atom, right? And they draw this big area around the atom. What do they call that big area? This is the electron cloud. The electron cloud is the place where you're likely to find an electron in an atom. We can't predict where electrons are going to be. We don't know their path, but we know basically where they hang out. And that's called the electron cloud. So you got to think that there's this electron that's zooming around, right? It's always moving. If you have two atoms that collide with one another, that electron is going to move away from the collision site. So then what happens to the electron cloud of two atoms that hit one another or hit the side of a container? They're going to actually move. So that's what I've drawn down here in red, right? We have this molecule and each X is an atom. So this is a 3-atom long molecule, whatever, doesn't matter. And it has an electron cloud. This is its original electron cloud. It collides with a wall, whatever. The electrons, so here's the wall, right? The electrons hit the wall and kind of bounce to the back of the molecule. So now we have an area where we have more electrons. It's an electron-rich area and an electron-poor area. The electron-rich area is partially negative, it's actually partially, and the electron-low area is partially positive because it doesn't have as many electrons there. So you have this temporary dipole, but an instant later, the molecule reorients itself back to look like this. So it's instantaneous, it changes, right? When you touch the wall, is the wall solid? No, it's not. Most of that wall is empty space. Most of you is empty space. Most of every single atom is empty space. What you are feeling is the electron cloud, and the electrons move so fast that it feels solid, but it's not. So cool, right? Things aren't really solid. Just blew your mind today, right? Okay. So you can have temporary and you can have permanent dipoles. Water is our example of a permanent dipole. And then anything that is non-polar, right, can only have London dispersion forces. Something like water has London dispersion and its permanent dipole. So everything has London dispersion. And then depending on the characteristics of the molecule, they can have additional attractive forces. Okay. So another type of attractive force is a hydrogen bond. A hydrogen bond is a dipole-dipole interaction. What did we just say has a dipole? Water, right? So if I have two water molecules and they each have a dipole and they're attracted to one another, we call them a dipole-dipole interaction, right? So you can have that dipole-dipole interaction with anything that is polar, but you can only have a hydrogen bond between an oxygen, right? That's a very electronegative atom. So between an electronegative atom and a hydrogen. So there are a couple of different electronegative atoms. Those electron-negative atoms are nitrogen, oxygen, and fluorine. It is no fun, hydrogen bonding. It's no fun. NOF, right? Look on the periodic table. Who's the most electronegative? Fluorine, that floozy, right? Who's next to fluorine, the floozy? Oxygen. Who's next to oxygen? Nitrogen. They are all electronegative. So these can pull the electrons from hydrogen, right? And hang out. So when you talk about hydrogen bonding, right? It's that force between your hydrogen that's already participating in a polar bond with another electronegative atom participating in another hydrogen bond. So let's talk about this. Let's talk about this. So if we have, let me do it this way. Let me do it this way. If I have this oxygen atom, and it's in a water molecule, right? This hydrogen's partially positive, partially negative, right? And it's got its lone pairs. If I were to draw another water molecule, what is going to be attracted to that oxygen? An oxygen atom or a hydrogen atom? A hydrogen atom. Because this is partially positive, partially negative. So my hydrogen bond is right here between my electronegative oxygen. So this is my electronegative atom. In this case, it's oxygen, but it could be oxygen, it could be nitrogen or fluorine. Right? So my electronegative atom, and then I have my partially positive hydrogen. If it's a hydrogen bond, you have to have a hydrogen involved. So it's a hydrogen with no fun. So in a hydrogen bond, we talk about some atoms being donors and some atoms being acceptors. So if it is a hydrogen bond, we're talking about the hydrogen. Which of these molecules, the blue or the black, is acting as a hydrogen donor? Who has the hydrogen, blue or black, that's participating in the hydrogen bond? The black. Black is the donor molecule. Now, which of the molecules is the acceptor that is accepting the interaction with hydrogen? The blue one. So this is the H bond acceptor. Okay, so now let's try to answer this question. Given that only polar molecules can participate as donors in hydrogen bonding, is it true that all polar molecules can be hydrogen bond donors? If I'm polar, does that mean that I can donate a hydrogen? If I'm polar and I have hydrogen, I can donate it. But is that all molecules? Do all molecules have hydrogen? No. So no, because not all molecules, molecules have a hydrogen, let alone a hydrogen that is partially positive, have a partially positive hydrogen. Right? That's the definition. In order to be a donor, you have to have a hydrogen that is partially positive. In order to be an acceptor, you have to have either an oxygen, a nitrogen, or a fluorine that is partially negative. Okay? And how can you tell if an atom is electronegative? Typically, it has these lone pairs of electrons, and the atom is nitrogen, oxygen, or fluorine. So you have to have lone pairs. Okay. All right. So consider your answers. Can water and carbon dioxide form a hydrogen bond? Explain. Tell me about, we know about water, right? Tell me about carbon dioxide. What is carbon dioxide? CO2. So how do I draw CO2? Take a second and draw it. Please don't pack up, y'all. We have 3 minutes left. Please don't do that. How do I draw carbon dioxide? Carbon likes how many bonds? 4. Lone pairs on my oxygen. I'm going to end up like that, right? Okay, now I have oxygen. I have my oxygen on my water, hydrogen, hydrogen. So can water and carbon dioxide form a hydrogen bond? Why not? Do you have a polar bond between carbon and oxygen? Do they have a difference in electronegativity value? Yes, they do. So if I drew a bond, a polarity arrow, what would I point at? I point at the oxygen because oxygen's hogging it, right? So I have a non-polar molecule, but I actually have polar bonds. So I have a partially negative oxygen, a partially positive carbon, and a partially negative oxygen. So my partially negative oxygen can make a hydrogen bond with my partially positive hydrogen here. So can I create a hydrogen bond? Yes, I can. Yes. So the partially positive oxygen in CO2 is donor or acceptor? What? Acceptor. And partially positive hydrogen in water is donor. We fit the definition, so we can do it. Yeah? Okay, see y'all next time.